Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Gwangeon Seong and Kyujin Kwak with us today.
Hi.
And I'm sure I
Hello.
butchered that Korean. I am sure I butchered that Korean. So you're very graceful in taking that. Thank you.
Okay.
And Gwangeon, let's start with you. What's your geolocation? Where are you located at?
Yeah, I'm in right now in Seoul, Korea,
Oh,
because I'm started a postdoc in Ewha Women's University at
cool.
in March. So yeah, I'm in
Okay.
Seoul.
Well, very good. So, well, congratulations, Dr. Song, on starting your first postdoc. Very nice. And let's see, it is March 24th of 2020, or it's my March 24th of 2025. It's your Tuesday, March 25th. And has spring started in Korea, or are we still in sort of our winter mode?
Yes, it's gonna be warm day, but the temperature difference between day and night is
Cool.
quite large, so
Yeah.
it it is easy to catch a cold.
Well, I'll cross my fingers you don't get one, okay? Oh, very good. And Kyujin,
Yep.
what is your position? And you're also in Korea, I take it?
Yes. I'm living in Ulsan area. It's a southeast coastline of the South Korea Peninsula,
Nice.
and I'm at the Ulsan National Institute of Science Technology. It's a long name. We call it UNIST.
Yes.
And I'm an associate professor at the physics department,
Very cool.
and I've been working on mostly astrophysics.
Hmm.
So partly
Mostly,
working on
what other things do you do besides astrophysics? I mean,
Well, sometimes working, we collaborate with the plasma physicist.
hmm
The lab works, but it's mostly theoretical work. And
hmm
recently, I got interested in like gravitational wave and the neutrino astronomy,
hmm
which is the
hmm
paper we are going to present. The Gwangeon been working on,
Very cool.
and Gwangeon used to be in my group. He recently graduated from Ulsan,
Very
so
good.
he moved to a bigger city. This is
Ah,
yeah. Okay.
well, I'm glad to see you're still collaborating on something
Oh
here.
yeah, of course.
Very nice. Very good. And that is going to bring us to this very awesome
Mhm.
APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Neutrinos from carbon burning red supergiants and their detectability. And Gwangeon and Kyujin, take us away.
Yeah.
Yes, so now I'd like to share a detail of these studies. So the main idea here is that by combining simulations of massive star evolutions and simulations of the neutrino detectors, then we can estimate the detectability of neutrinos emitted from the specific target. In this case, we are focusing on the carbon burning phase of massive stars as
Okay,
future source of neutrino astronomies.
cool.
So the overall flow of this study is quite straightforward. So first, we present simulations of stellar evolutions and calculation the corresponding neutrino energy spectra. Then we simulate neutrino matter interactions and focusing on the interaction between neutrinos and electrons.
Okay.
And
Mhm.
also based on those interactions, we also simulate the subsequent photon emissions and detection processes.
Cool.
So,
I'm
the neutrino detectors considered in this work is a water-based liquid scintillator, so
mm,
which is regarded as the one of the next generation detector candidates.
Yep.
And we focused on this hybrid type because currently operating detectors have some limitations to observe neutrinos with both signals and direction in sub-MeV energies.
Okay.
So according to our calculations and previous studies, so late stage of massive stars is expected to emit neutrino in the sub-MeV. So that's why we aim to explore the feasibility of detecting such low energy neutrinos. And so as a result of our simulations, we find that in an idealized model hybrid detectors with 50 kiloton size, a
Okay.
neutrino from a carbon-burning star located at a distance of 200 parsec would
Okay.
generate about up to the 50 detectable events for 1 year, over 1 year.
Wow.
So, however, our conclusion is that unfortunately, despite these potentials, there's remain many hurdles to overcome in order to detect them. So,
Indeed. Cool.
yeah. So next, let's dive into the detail of the studies. So
Okay.
first of all, let me discuss how to detect neutrinos, focusing in particular on MEV energy neutrinos.
Okay.
So MEV neutrinos are mostly observed using underground neutrino detectors, which can be broadly divided into two main types. So one is the scintillate type, and the other is Cherenkov type. So
Yes.
each type has its own pros and cons. So scintillate types can detect neutrino by observing the light produced from the elastic scattering
Yes.
of the neutrinos and electron in the scintillator. So in this case, even if the recoiled electron has low energy, the scintillator can generate a lot of photons, so allowing for the detection of low energy neutrinos. So, however, since the scintillator emits photons isotropically, so it is generally not possible to determine the direction of incoming neutrinos. So, and additionally, scintillator detectors typically have a small size, and on the other hand, Cherenkov detectors use a light generated by recoiled electron in water,
Yes.
so it's gonna be possible to estimate the direction of incoming neutrinos by reconstructing Cherenkov ring.
Yes.
But in this case, recoiled electron requires much higher energy to generate enough photons to detect the neutrinos.
Okay.
But if neutrinos have a sub-MeV energy, then the recoiled electrons have not enough energy to generate a lot of Cherenkov photons.
Okay.
So, furthermore, other radioactive materials in the water can emit a lot of neutrinos in this energy level. So it makes it extremely challenging to detect them. So
Yeah.
for this reason, we considered water-based liquid scintillator in this work. So we believe this is good choice to detect sub-MeV neutrinos because this type of detector can get both signals from low energy neutrinos and direction of incoming neutrinos by combining scintillation and Cherenkov radiations. So directional information of incoming neutrinos is generally not only give us a direct evidence of neutrino source, but also help remove background signals.
Yes.
So in this work, in order to estimate detectability, the first step is to calculate the amount of neutrino flux reaching Earth from the source.
Yes.
And for this, we used MESA to simulate the evolution of several massive stars and also to calculate neutrino luminosities.
Okay.
So I refer in this work the MESA list file published by Ebrahim Farag. I don't know how to pronounce his name actually.
Faraj.
Sorry.
Well, that's okay.
Yeah,
I butchered your Korean name, so you can butcher his name.
okay.
But it's Faraj.
So for this simulation, and I noticed that it was created by you, Professor Frank Timms. So I really appreciate for you and Ibrahim Farag. So these results are presented in the figure 1. So
Okay.
the
Let's go to
the
figure
figure 1.
Okay, looks like we got some HR diagrams.
Yeah, the left panel shows the convolutional HR diagram of our massive star models. And the right panel is their corresponding the neutrino HR. So in this figure, the dark lines in the left diagram represents the carbon burning phase of the massive stars.
Okay.
Massive star candidates within 1 kiloparsec are indicated by circles. So in the and
Good. Okay.
yeah,
Okay.
and in the right panel, the carbon burning phase is highlighted by a dark dashed lines.
Nice.
So
Okay.
keep going. So in the interior of stars, they produce neutrino through two main processes. One of through nuclear reactions, which dominated during core hydrogen and helium burning phase. However, from the carbon burning phase, a lot of neutrinos generated by thermal processes and become more dominant than those processed by nuclear reactions. So figure 2 shows the energy emitted by thermal neutrinos in the carbon burning phase. So particularly 30 solar mass models.
Hey, I'm with you. Yep.
Yeah, from this figure, we can see that the pair annihilation process is the largest contributor to the neutrino production. So,
Yes.
and next, to calculate the neutrino flux reaching Earth, so we need to know energy of each neutrinos. So in other words, we have to calculate neutrino spectrums.
Yes.
So the reason is that the cross-section of neutrino interaction is function of neutrinos energy, and the recorded energy of interacting electrons depends on the neutrinos energy.
Okay.
Also, so as shown in the figure 2, so because the pair annihilation is dominant than other processes, so we consider only the spectrum of pair annihilations in this work.
Okay. Okay.
And to calculate the neutrino spectrum, so we referred to the equations derived in Kato et al. And we outline this equation in equation 1 of our paper.
Let me get there. Just take a peek at what we got here. I went too far. Sorry.
Yeah.
My bad. There we go. Equation 1.
Yeah.
Parallel.
And
Yep.
yeah, from these equations, so we estimated neutrino spectrum during the carbon burning phase, as shown in the figure 3. And additionally,
I'm with you.
yeah, additionally, so considering a distance of 200 parsec neutrino oscillations, so we also plotted the neutrino flux reaching Earth in figure 4.
Okay, so there's our spectrum. Okay, I'm with you. And those are different radii. Okay,
Yeah.
good. I'm with you.
Yeah.
Okay, figure 4. Let me get into the fluxes at some distance. Yes, 200 parsecs.
Yes.
Okay.
Oh, sorry, my stereo is working.
All good. All good.
So, and this figure shows the flux at Earth according to the different mass hierarchies of neutrinos. So
Okay.
our result indicates that in the normal hierarchy, anti-electron neutrinos dominated, while in the inverted hierarchy, anti-tau and mu neutrinos are more important.
Yes.
But interestingly, the difference due to the hierarchy of fear to almost vanish in other factors. So let's see in the next part.
Okay. Okay.
So next, I will talk about the third part of this paper. So about the detector simulations. So
Yes.
these simulations was performed using two parts. The first part is simulation of neutrino electron interaction with using Monte Carlo method with neural code.
Okay.
So our results show that elastic scattering between neutrinos and electrons is the dominant reaction in the energy range of our interest.
Okay.
And figure 5 shows the cross-section of this interaction as function of neutrinos energy.
Yes.
Yeah, with different colors and lines representing different neutrino types.
Mm-hmm.
And
all of it, mu's and tau's, all of them. Yep. Uh-huh.
yeah. According to the figure, the cross-section is largest for electron neutrinos, followed by anti-electron neutrinos is about one-third of that value, and with the remaining neutrino species having approximately 1/10 the values.
Yeah.
So this difference is the primary reason that the mass hierarchy effect is migrated.
Okay.
And so also, and from the result of neuro, we could obtain the momentum of the recorded electrons. So in other words, it's energy and direction of recorded motions.
Yes.
So using these two properties as input parameters for another simulations, and we performed the neutrino detector simulations using GANT4.
Yes.
And these simulations consist of, this simulation consists of two simulations. One is the photon emission when the accelerated electron interact with the water-based scintillating material. And the other is subsequent detection of those emitted photons by photodetectors equipped at the wall.
Yes.
So
Okay.
So in this simulation, so we set the detection criteria, and the criteria for the detection are detailed in the main text. So please refer this main text.
Mm-hmm.
As a result, so we plotted the detector's detection efficiency according to this criteria in figure 6.
Yes.
So interestingly, based on our simulations, so there's no difference in detection efficiency between mixing the materials with 5% versus 10%.
Yes.
And
Cool. Very nice.
And now combining all results, the expected number of detectable neutrino events are shown in the figure 7 as function of neutrinos energy.
Mm-hmm. Equation 3. And there we
Yeah.
go. Event rates.
Yeah, this is figure 7 is calculated by the equation 3.
Yes.
Yeah.
Mm-hmm.
So, and also in this figure, we plotted CNO and boron neutrinos from the sun, and which have a similar energy range.
Yeah.
And we also included the noise signals that might occur in the detector. So
Okay.
in this figure, the 5% of LIB model was used as the baseline for the detector, and expected number event for neutrinos from carbon burning phase have at least 1.1 detection event per year at the
Yeah.
early stage of carbon burning phase, and we up to about 50 events per year at the end stage of the carbon burning phase. So
Very cool.
for so for cyano neutrinos, we estimate that the detector could see about 10 to the 5 events per year,
Okay.
and the number of radioactive background signal is unfortunately expected to be around 10 to the 8 events per year.
Right.
So
Right.
this number shows getting a signature of neutrinos from nearby carbon burning star seems to be challenging with current model detectors. So,
I'm an optimist.
yeah.
Yeah.
Next, another result I want to show is the angular resolution of our model detector. So, oh my God! So I missed a lot
Yeah, I
of
think you want to cover
detail.
this one.
Yeah. So in the water-based liquid scintillator, the main idea of getting direction information is to separate the chunk of photons and scintillation photons. So in
Okay.
general, so chunk of photons are produced earlier than the scintillation photons.
Ah,
So
yeah.
it means that it is hit earlier at the photodetectors. So as shown in the figure A. So
Yep. You
so
got the peak coming in well before
yes,
scintillation comes in. Mm-hmm.
yeah, but the time gap is almost 0.1 nanosecond. So that's the key factor of this detector is time resolution of photodetectors.
Cool.
So there are so to do that, so there's an examples for this ultra fast photodetectors such as LIPPD, and in
Right.
progress for developing technologies to separate chunk of photon and scintillations and so on. So anyways, so it is possible to if we how can I say? So if we can separate chunk of and scintillation photons, then we only use chunk of photon to find the direction of incoming neutrinos.
Yeah. Okay.
So using the scintillation photons, we can get the signals and we can get the direction informations to use only chunk of photons. So
Mm-hmm.
So I would say that this is a good example that the science drives the technology. So
Yes.
in order to detect the cosmological or astrophysical neutrino,
Mm-hmm.
we need to develop the high resolution temporal like photodetector in
Okay.
order to separate this Cherenkov and scintillator light.
Yes. Very good. Cool.
so yeah. And the last figure, last table
Angular resolution.
shows
probability distribution functions.
Yes.
Yeah.
So
Mm.
and this figure and next table. So
Yep.
table in the shows shows that our test for getting angular resolution of modern detectors. So
Cool.
from the test, we confirm there's a 43% chance
Yes.
that the event can be reconstructed with 60 degrees.
Mm-hmm.
So we regard that in our modern detectors, the angular resolution for detecting sub-MU neutrinos on the order of tens of degrees. So,
Okay. Cool.
yeah.
Why is
So
I'll just ask the question. Why isn't the curve symmetrical about 0?
because actually that the reconstruction is not perfect because if neutrinos comes into the detectors, then the required yeah. So how can I say? So if
Forward
if
scattering?
if
Forward scattering.
if neutrinos hit the electrons, then the scattered electrons is not linear to the neutrinos because there's some scattering angles. So
Yes.
because of them, so the reconstruction is not perfect because of that angles. So
I'm with you.
yeah,
Thank you.
that's why this figure is not normalized as the 0.
Okay.
Okay. Yeah.
I got it.
So
Very good.
yeah. So anyway, in conclusion, so in this work has showed the potential of the hybrid detectors in future MEB neutrino astronomies. So while our simulation result based on the 50 kiloton detector
Right.
indicates the nearby carbon-bearing star may not be ideal new targets.
Yes.
But the sun or pre-supernova neutrinos present promising opportunities. So therefore, we plan to continue our research, and we look forward to presenting more advanced results in the future. So.
Okay. Very good.
Yeah.
Beautiful work. Beautiful work. And I just wanted to loop back to table 1 because it's always nice to have observational targets or experimental targets for these things. So what are we talking about here? So yeah, Betelgeuse on Paris. So these are some of the prime red supergiants that are within a KPC or so.
Yeah.
Very
I would say that the number one, the Betelgeuse, the beloved target of is a good candidate for the next supernova explosion.
Yes.
No, so we are basically our motivation is whether we can detect if there are the neutrinos emitted from Betelgeuse if it's in the carbon burning stages.
Correct. Okay.
That's our like a fundamental motivation, whether maybe the next generation the hybrid detector can observe or not the neutrinos from the Betelgeuse. So, but it's not that optimistic, even though I try to be optimistic, but
I'm good. It's like gravitational wave detection, right?
oh yeah.
There's certain similarities between those two, and so neutrinos are just a little bit behind gravitational waves. So very good. All right, that was awesome. Gwangeon and Kyujin, I want to thank you so much for walking us through your very lovely article. Great. And you mentioned it a little bit there, so let me go ahead and toward the end. So let me go ahead and push on that a little bit and ask where do you think we go from here, given the published article? Is there well, there's always more models to run. We can do that. Is it worthwhile going and looking like oxygen burning, something like that? Are there targets to give some of the experimentalists on maybe the next generation type of neutrinos? And just sort of next steps. Where do you think we go from here, given the published article?
Gwangeon, you go first.
Yeah. Uh, maybe I'm planning. I am planning to studying the first the CNO neutrinos from the sun. So is that because that is the similar that has the similar energies. Yeah.
Okay. Very good.
So actually, he's working the two projects at the same time now, and we are still collaborating. So one is the, as you see in the figure, that the CNO neutrino from the solar CNO neutrino has much higher flux than the red supergiant neutrino. So in order, in terms of the detectability, it's better to calculate the CNO neutrino detectability out of our current hybrid detectors. So that's one way of the ramification of the current work. So he's working for calculating the detectability of the CNO neutrinos. That's one thing. And then the second thing, like you mentioned, is we extend our carbon burning stages to the oxygen and silicon burning, which is expected to emit more fluxes.
Be even larger.
So it increases another detectability. So there are two, like, how can you say that? Simultaneous.
Parallel.
Yeah, parallel. Yeah.
Very cool. Very nice. Well, it'll be really exciting to see this develop over the next couple of years, particularly on the detectability front. It'll be really cool. Very nice. And I look forward to seeing it go through.
Okay. And then we are also interested in building the real detectors because Korea is involved in like the second tank of the hypercamionkan, which is under construction. So the budget-wise, the Korean version of the detector is still in the infant phase. We're still trying to find the fund, but we are also aiming to construct our own detector, aiming to detect like maybe the hybrid detector. It's a different design than the hypercamionkan.
Very nice. Very nice. Well, that's very exciting to see. Very nice. Cool.
And then we need to say about our co-authors, the Dongsu Ryu.
Let's get them up. Let's give them a proper shout out here. So Dongsu.
Yeah, so he's actually the senior researcher in our group, and then he's a theorist, but he's a key person to push the new detector, the Korean version of the hybrid detector, like maybe a similar version to the hypercamionkan, or maybe the different one. So he's like a core. It's in the core member to push the new detector, and he's also helping us the calculation. And then Gwangeon, he actually started the simulation of the detectability, GNT4. And then the Gwangeon took over his calculation for some way because he left the group and then he joined the working with the new. So he's now working for the accelerator in Pohang. It's an X-ray accelerator, X-ray laser accelerator. Kind of switch it to the new field.
Good shout out. Good shout out. Gotta get all your co-authors in here. Very good. Awesome.
Okay.
Gwangeon and Kyujin, I want to thank you so much again for walking us through your very awesome article. Thanks.
Yeah, thank you for having us.
Thank you.
We enjoyed the time. Okay.
Yeah.
And that'll do, everyone. And I hope this made your neutrino astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye. Thank you.
And